Hello, friends, and welcome to Simulab Insights. Today, we're going to explore a fundamental topic in power electronics, the single-phase full-wave controlled rectifier. We'll walk through how to model this circuit step by step in MATLAB/Simulink and observe both the input and output voltage waveforms through simulation. This session will help you better understand the working and analysis of controlled rectifiers, which are widely used in power electronic applications. So, what is phase-controlled rectifier? Let's understand the basics. A phase-controlled rectifier is a type of rectifier circuit that uses thyristors, SCRs, instead of diodes to convert AC, alternating current, into DC, direct current. The key feature is that the output voltage can be controlled by adjusting the firing angle of the SCRs, that is, the point in the AC cycle when the SCR is triggered. By delaying the firing angle, we can control the average output voltage, making phase-controlled rectifiers useful in applications like motor speed control, heating control, and variable DC power supplies. Let's walk through the simulation of a single-phase full-wave controlled rectifier in Simulink and understand how it works. To begin, we need to add the essential components required for building the circuit. You can do this in two ways: by using the library browser or by double-clicking in the Simulink workspace and typing the component names directly. To simulate a single-phase full-wave controlled rectifier, we will need the following components. Thyristors. It is used to control the conduction period by triggering them at desired firing angles. AC voltage source. Pulse generator. It generates gate pulses for triggering the SCRs at specified times. Series RLC branch. Voltage measurement block. It measures the voltage across load. Scope and power GUI block. Once all the components are added to your Simulink model, the next step is to connect them to form the complete single-phase full-wave controlled rectifier circuit. After that, configure each component, like setting pulse generator timing, source amplitude, etc., and then run the simulation. Connect the thyristors in a bridge configuration, ensuring that each pair of thyristors is connected to the AC supply terminals. Next, connect a resistive load across the output terminals of the rectifier circuit. To control the conduction of the thyristors, connect the pulse generator such that it provides appropriate gate signals to trigger the thyristors during both the positive and negative half cycles of the AC input. Connect the voltage measurement blocks across both the load and the AC source to monitor input and output voltages. Then, connect these measurement blocks to the scope to observe the rectified output waveform. Now, Configure the pulse generator block. Since the AC supply frequency is 50 Hz, the period of the waveform will be 0.02 second, which means one cycle of 50 Hz completes in 0.02 second. To generate proper firing pulses for the thyristors, during the positive half cycle, thyristors T1 and T2, and during negative half cycle, T3 and T4 should be triggered. You can achieve this by setting appropriate phase delays in the pulse generator.
As we can observe, one complete cycle of the AC waveform is completed in 0.02 seconds. The output voltage is rectified during both the positive and negative half cycles, confirming the operation of a full wave controlled rectifier. This demonstrates its higher efficiency compared to a half wave rectifier, which only rectifies the positive half cycle of the AC input.